Congratulations, you have made it to the last topic. This is the end of the semester, and this is the last topic we're going to be learning with in Python. So we're doing Pearson correlation, and so that is trying to see if two quantitative variables are correlated. And I know we've already looked at scatter plots, so we can sort of see a little bit whether the dots line up in our scatter plot or not. But this is going to do an actual hypothesis test and get a lot more information for us. So the first part, that's a little bit annoying, but it has to be done, is when we look at just these two variables. So here are my quantitative variables. Sibling number was my explanatory, and diagnosis age was my response. And when we look at it, this makes sense. Diagnosis age only is going to be there if the person had asthma, and less, like way less than half of the data set had asthma. And so a lot of these rows, a lot of these people in the data set have a NAN in there. And so we have to kind of throw away those rows and not have the data set look at them. And unfortunately, the commands we're using don't do that automatically. Like when we did a scatter plot, it just didn't plot these points. If it had a NAN in it, it just ignored it. And that's true for a lot of the things we've been doing. But for this regression stuff, unfortunately, we have to just delete those rows. And we don't want to delete them out of DF, our data frame. That would, throw away a bunch of the data we're looking at for our other variables. So here's what we're going to do. We're going to make up a whole new data frame called clean data. So we're going to clean up our data frame. And it's going to be the original data frame, but just these two variables. We're going to throw away all the other variables for just this CD thing, and we're going to drop the nans, drop NA. I know there's no N at the end of that. If I were inventing this, I'd say drop NAN, but it's drop NA and then the parentheses. And once I run that, if I look at it, it no longer has all the nans. And you'll notice that the very first one is index 13. Index 13 was the very first one that didn't have a NAN. So there it is, the 1,12. There's 1,12. Okay, so it's cleaned up. My scatter plot, I just copied this from when we did it before, making sure that fit reg is true so that I can see the best fit line. And there it is. And, when we talked about this before, we said, I bet there's no correlation here. There's probably not an association at all, because this line doesn't seem to be following any trend. Okay, maybe it's the best line that is possible, but it doesn't look like a very good predictor for where these dots are. It just seems like a blob of dots that you threw a line through. Well, let's see. Let's run a hypothesis test. So this is a bit of a confusing block. You have to do an import. This thing SM, standing for stats models. And then I'm using CD. So that's that new data frame that we created up here. There it is, CD. And I'm saying that the Y variable is CD diagnosis age. That goes with what we said. That's going to be our response variable. And the X variable is CD sibling number. And then you have to say the X is sm.add underscore constant of this X that you created. So this is putting a little bit of extra on your X variable. And then you make a regression equation with this line. And then print out the summary for that regression equation that you created. All right, it's a lot that this is going to do. Check it out. Shazam. All sorts of stuff. Now, the part we're going to look at is the R squared. And so we're going to make some sense out of that. The F statistic is just like, T statistic or anything else. It's the number that it calculates that it's then going to see how rare that would be if there's no correlation in the population. What are the chances we get this blob of dots like this? Oh, pretty high. Or even more scattered blob. 62% chance. Way bigger than 0.05. This 0.621 is way bigger than 0.05. So, yeah, we have no evidence to say these are associated. So, all right. If this happens, I don't want you to go on with your variables. If you don't have a p-value less than 0.05, then you're done with your variables. And you have to go to these variables that I've got that definitely have a correlation. And so you will have access to some of the data management and stuff for these. So don't worry about that. And so I'm going to look at them. And what these are is the height in inches and the weight in pounds. And so you've got all these ordered pairs. I don't see any NAs, but I'm going to go ahead and make CD2 out of dropping the NAs and just having those two variables, just to be sure. I'm only looking at the top 20 rows out of thousands and thousands. There may be some NAs in there that now are gone. Here's my scatter plot with the regression line. There it is. And in this one, we can kind of see that trend that the taller you are, on average, the heavier you are. So, there's other stuff involved in that, but that's the trend. Now, is it a close enough trend? Is it really, that's saying that these are correlated? Well, I need to look at the p-value. So I go through and I do this once again, and it's okay that I'm wiping out X and Y and reusing them, because at any time I do this, it will be, if I want to do it again and get this whole thing again, I'll run this and repeat the X and Y and it'll be fine. I don't need to import the stats model again because it's already imported, so I didn't do that. But when I run this on these two variables, now my R squared is not 0. And so what this is saying is that 19.4% of your weight can be predicted using your height. So the other 80 some odd percent, this is about 20%, so the other 80% is other factors. There's other stuff going into how heavy you are besides just your height, but 20% of it is predicted by just your height. Okay, so that's how I can interpret that R squared. And then what about the p-value? Holy smokes. So the chances, if these two aren't related at all in the population, the chances I would get a sample where they're related this much, or even more tightly related than that, the dot's even closer to the line on average. E minus 237. Please don't make me write 237 zeros in front of the 5. Basically 0. Basically no chance we would get these lining up this much if they didn't line up at all in the population. Okay, that is a significant result. Now that we have this significant result, we've got a chance to use this line to make a prediction based on somebody's height. Predict how much they will weigh. It's not going to be perfect. It's only 20% of your weight is predictable by your height, but we're going to use this line anyways. Okay, if you're actually going to use your regression line to make a prediction, like if you're trying to predict the weather or something, or what the global temperature is going to be in 2050, if things keep going the way they are, stuff like that, you want an R squared bigger than just 0.194, right? But we're going to just use this just for practice. And so what we need is to so what I'd like you to do, and I'm gonna just take this first point here, I'd like you to use another one. So for one of your slides, you're going to show what is the error if I use 71 as my input in my model and try to predict the weight based on the model and a height of 71. Does it come out to 238? If it comes out exactly, you got no error. But if it comes out to something different from 238, we're going to calculate by how much is it off. Okay, so you may remember that for lines, and this is linear regression, so it's a line, the y, the output, is equal to mx plus b. But where am I getting this m and this b? Here's my y equals m times x plus b, well, I have a minus because it's a negative b. Where am I getting those from? Right here. There's the b, minus 167 point, I just rounded off to 2 decimal places, 0.29, and there's the m. Now it's labeled with the y variable, right? The height's our output variable. I'm sorry, it's labeled with the input variable, my bad. It's labeled with the input variable, but it's the slope. There's the slope that I grabbed. And so what I did is I said, all right, I'm going to use this formula to calculate what the weight would be, according to this formula, if the height is 71. So I took the x value and I plugged it right in to where the x is in this formula, and I multiplied it times 5.21 and then subtracted off 167.29. And I let Python do it. And so Python gets 202.62. So if you're going to be right on this line with a height of 71, then your weight is going to be predicted to be 202.62. So that's different from what we observed. So we're going to see how different is it. We're going to calculate the error, which is going to be what we got with the calculation using the sit line as the way to predict, and then take away the observed, and we have an error of negative 35.38. And that's just saying that what was predicted is below what the observation is by 35 pounds. All right, that is plenty. Thank you for all your patience throughout all these videos. Of course, we'll go over this in class as well. And have a great day.